And the last type of surface integral we're going to take is a surface integral using parameterized surfaces. And these are going to look kind of messy, but they're a little bit easier because you tend to be given more of the information to start. But a parameterized surface is just like we learned how you can write curves using a vector r that depends on only some variable t. Parameterized surfaces can also be written as a vector. So you have some vector representation of spinning over the surface, but it depends on two variables because surfaces have two dimensions, whereas curves only had one dimension. So that's just to help you kind of like visualize what parameterized surface means. So to do a parameterized surface integral, you should be given the parameterization r, which is going to kind of tell you like your x component in terms of two unknowns. And just like when you had r equal to x of t, y of t, z of t, you had bounds for t. You should be given bounds. Actually, no, we'll just do. Actually, they don't even have to be function or constants. You should be given bounds for u and v. And if you're not given it in vector format, you just have to plug the different components into the vectors, but it should be pretty straightforward. So you're given that, I guess, identify it, that you know r is the thing that looks like a vector, and the bounds you need are the things they tell you about u and v. And then you're going to identify your function or vector field. Little f or capital F. And substitute your parameterization. So everywhere you see x, y, or z, you replace with u and v using your parameterization at the start. Then from your parameterization, you're going to compute like the partial derivatives in all the components, r sub u and r sub v. I'll go ahead and I'll write the formula. So r sub u would be like you take d du of x of u, v, dd, okay, d du of y of uv, and d du of z of uv. And r sub v is going to be the same thing, but using partial derivatives with respect to v. I'll put little tails on these u's. That way you know that that first one is u, the second one is v. So you compute those partial derivatives, And then you compute a cross product, unfortunately. So you compute R sub u cross R sub v. And then you can evaluate your integral. So over the scalar value function, it's going to be f times the magnitude of R sub u cross R sub v. And then for the vector field f, it's going to be f dotted with, I'll do it in parentheses like this, R sub u cross R sub u cross R sub v, but also integrated over du dv. And on these integrals go the bounds for u and v. So for example, I'll say that I put u on the inside, so your v bounds are the ones that are constant, and your u bounds could depend on v, like that. The notation is making this look more complicated than it is. Really, it's going to be somebody gives you the bounds for u and v, and you just have to set them up like a normal 2D integral. I know that this like function notation can be overwhelming. So if it's easier to just like for now think about that not being there, and you just know their integrals with respect to u and v, and you're going to fill them in, that's okay too. But these are the steps you'll use for parameterized surface integrals.